I'm here with Alex, who is the Fast Plasma Investigation Operations Lead for the Magnetospheric Multiscale mission. How you doing, Alex?
Good to be here.
Now tell me, when it comes to engineering, what is your job? What have you done with the MMS program?
So I've actually been on the MMS program with FPI since 2007. My day-to-day job is making sure the instruments keep running. So looking at the data coming down, checking all the voltages, the currents, making sure that we keep them operating as long as we can. And that includes calibration, it includes processing science data, any kind of anomaly. If we see a spike in a number or a dip in a number, we trace that down, find out root cause, and interfacing with the spacecraft, the other instrument teams.
How is the fast plasma investigation operating in orbit, compared to the way it was when you tested it here on the ground?
It is almost exactly the same. One of the things we were very happy about is how closely the instrument performs in flight as it did in ground testing. The calibration matches up almost perfectly with the ground calibration. The science coming through looks great. We did an unprecedented amount of simulation, testing, everything we could on the ground to ensure that we'd have a good run in flight, and so far that's been the case.
While the spacecraft are flying, you're trying to take a picture in time of what's happening. How do you do that and keep those spacecraft calibrated to do it the way you want it?
This is one of the hardest things that FPI has to do. So previous plasma measurements have done what we call a spin-integrated measurement. So it's like if you have a camera and you do a panoramic where you just slide the camera around like this, and as you spin around, you slowly take the entire image. And that takes 5 seconds. On FPI, we need to capture the entire sky in 30 milliseconds, so 100 times faster than any previous mission. So we actually have 32 cameras, if you want to call them cameras, simultaneously capturing data. And we need to stitch all of those together into one set of images. And that's the hardest part of this calibration, is making sure when you put all these things together, there's no discontinuity, there's no offset. Everything looks perfectly smooth when you look at the data at the end of the day. The orbit of MMS in this phase is just shy of 24 hours. 12 hours of that are prime science, what we call the region of interest. Another few hours are in the radiation belt where we're low voltage, but several hours of that orbit are actually devoted to calibration. So we have several different calibration activities we do, and each one looks at a different thing. So we have one calibration that makes sure the voltages are set properly. So if we say, I want 100 volts here, we make sure it's 100 volts, not 110 volts. Another one of those looks at making sure we pull out only signal and not noise. So filtering out the chatter and keeping the good science. Once we get calibrated, we then have to choose which data comes down. MMS as a whole only takes down a small percentage, like 2 or 3%, of the total high-resolution science data that we capture. And that's just a function of, as I mentioned, we're measuring so fast, and the antenna can only bring so much down. So we have to choose which data is the most scientifically valuable and prioritize what gets pulled down and what gets left.